This is mini lecture number 6. And today what we are going to cover, we're going to continue on nodal analysis for DC circuits with no voltage source. What I want to do in this mini lecture is do a little bit of a recap. What is the procedure for DC circuits that do not have voltage sources? And then I'm going to do an example with you, a pretty substantial example, discussing what I think are the key point. And when I say the key points, I try to discuss what, in my experience, I've seen students having difficulty doing. I try to essentially preempt that so that you don't fall into the same pitfalls, essentially. And then I'm going to put a problem for you to do. And as I did in the past, when I put that problem, I'm going to ask that you either pause the lecture or stop it, and then spend about 25 minutes or so working the problems, and then come back and look at the solution. So that's pretty much the mini lecture today. This mini lecture will essentially end the nodal procedure for circuit without voltage sources. So let me share screen here, and let's go to the document camera for our recap, if you will. And hopefully the gods of the document camera will be kind to us today, not freeze. So what we're talking about here, we're talking about nodal analysis. For DC circuits. With no voltage sources. Okay. That's what we're talking about here. The first thing that when we talk about nodal analysis, I want you to pay attention to the term node, which is where nodal comes from. Okay. It is central to be able to identify nodes correctly. That's the method is based on the nodes, as we'll talk about essentially as we outline the procedure. So what's the procedure here? The first major step is what we call preparing the circuit. So what are we talking about preparing the circuit? The first step is identify all the nodes. And I'm going to put an emphasis correctly. Okay. If you don't have the nodes correctly, the entire procedure falls through. Okay, so it's actually a pretty basic step to identify the nodes. And we talk about using your pen and following the wire. As long as you don't cross an element, you're on the same node. But it is crucial that it is done correctly. Identify all the nodes. The second step is we select an arbitrary reference node. And when we do that, we're saying that reference node has a voltage 0 volt on it. Okay. So, and we put the symbol, either this symbol or this symbol, as indicator of which one is our reference node. And I really am talking about an arbitrary reference node. It really doesn't matter to the solution which one you select. Okay. The next step essentially is we label the nodes that are not the reference. Okay. And typically I suggest to say label them V1, V2, V3, and so on. In essence, I just don't want you to duplicate any node voltages. Now, make sure that there is not a V1 in the circuit already or V2, no duplicates. That these are unique labels for the nodes. Okay. So key point here, node voltages are the unknowns in the problem. Okay, so typical things I'm going to say, how many nodes we have, you're going to tell me n nodes. 3, 4, 5. And then I'm going to ask you how many unknowns in the problems. You're going to tell me n minus 1 unknowns. Okay. The reason that I asked that question, it's because it should give you a hint how many equations you need. If you have 3 nodes beside the reference node, so 4 nodes, 3 unknowns, you need 3 equations. So that already clues you in terms of how much work, how much equations you need to determine here. So label the nodes that are not the reference node. The next step in preparing essentially is insert current. And when I mean current, I mean label an arrow on each passive element. The only passive element we've seen thus far is the resistor. That has no current. So if a resistor has a current, don't add another current to it. That's the point that I'm saying here. Okay, if it has a current, use the current that the problem statement gives you. Okay, so this right there is what I call preparing the circuit. We haven't done any mathematical formula, any equations, anything. We've basically been preparing the circuit for solutions. Okay, the next step 2, we write KCL equations at each node that is not the reference. And KCL should be in terms of currents. In other words, I don't want to see anything except a bunch of currents in that equation here. Okay. So if you have 3 nodes beside the reference node, I'm going to see 3 KCL equations. Then I want you to step aside and write the resistor currents in terms of node voltages. Basically, Ohm's law. And when you're using Ohm's law, be very careful, be mindful of passive sign conventions. So when we write Ohm's law, we assume current entering in the positive terminal of the voltage. And then step 4, use the Ohm's law equations into the KCL equations and collect terms. Okay. You should at this point get 3 equations for 3 unknowns, 4 equations for 4 unknown, and that should essentially, you should be able to go to your calculator and to calculate the node voltages then. We're going to practice this on 2 problems today. Let me stop sharing here. We're going to practice this essentially with the problems that's pretty substantial. So let me show it to you, and then I'll start talking about it. Let's go to the PowerPoint slide. So here's our first problem that I'm going to do and discuss. And then obviously I'm going to put 1, hoping you spend time doing that. Okay. So this example is pretty solid example. One of the things that it has a dependent source. Okay. So this is, I think, one of the few examples we started by including dependent source to be more complete. Again, if you haven't had that much familiarity with dependent source, anytime you have a diamond shape in the symbol, that should tell you have a dependent source. Dependent means it has an output that depends on something else. Okay. The fact that you have an arrow in that symbol tells you it is a current source. Now, remember, dependent source can depend on anything, can depend on voltage, current, or combination of voltage and current. In this particular case, you have a current source, so it puts out some amperage, but the amount of current it puts out is, and that's given to you in the problem statement, it puts out a current that's 0.2 times the voltage VA, which is a voltage essentially between the one. That's a given statement. That's a given statement in the problem, in the problem statement. Okay, so your part is to identify that it is a current source and it is a dependent current source. That's your part. And again, we identified it's a dependent source by nature of the symbol being a diamond. And the fact that it has an arrow in it, you now know it's a current source. And be mindful, it can depend on anything else. Okay, so this problem is asking you to find VA and find the power absorbed by the 6 ohm resistor on top. So if we follow the discussion that we just had in terms of remind you what are the steps, and let me just quickly show you that again. These are the steps that I'm talking about here. We're going to execute this thing to the letter. I'm going to essentially identify the nodes. I'm going to select the reference node. I'm going to label the other nodes, and then I'm going to insert current, which means label an arrow on every resistor. And when I do that, keep in mind that the direction of my current is totally arbitrary. I can do left to right, right to left, up or down. There is no right direction to selecting the direction of the currents. Okay, this all comes out nicely when I apply Ohm's law, which is right here when I do Ohm's law, and I apply the passive sign convention. So no matter what I select for the direction of the current, when I apply the passive sign convention, it all synchronizes nicely into a correct solution. All right, so that's the point that about following these conventions. Okay, so let's go back to the PowerPoint slide. Okay, so before I start working, showing you some steps, the solution steps on the PowerPoint, let's doodle on this thing here. So one of the first things when students start taking this course, some students struggle with identifying the nodes correctly. They find more nodes or less nodes than they actually are. So what I tell you essentially, start at a point, at any point that's connected to an element. Okay, we start like this, and then we keep going on wires. As long as we're on a wire, it is the same node. As long as we're on a wire, until we touch an element, then we have the same node. Okay, so right there is the same node. Right there is the same node. Right there is the same node. See, I haven't crossed any element. So that's one node. So again, I suggest you take your pencil and just trace. As long as you're on a wire, you have the same node. As long as you're not crossing an element, you have the same node. So I can do that here. I can start, for example, here. Okay. And then I can go down here and I'm on a wire. All right. So I have the same node. Wire, I have the same node. Okay. I'm on a wire here. I have the same node. Okay, right there. So that's another node on the right. So you see, generally the nodes are not going to be nice dots. So you're going to have to identify them correctly because you're getting the hint that the node voltages are voltage at these nodes. So if I don't have the nodes correctly, obviously my entire solution fails. And finally, at the bottom here, I can start right here at any element at the bottom. Then wherever I'm on a wire, I am in one node. Okay, until I touch an element, I got one node. So of course, I'm not going to do this often because I'm assuming as you do 2 or 3 problems, this becomes pretty natural to you. But finding the node exactly is essential in this procedure. Okay, so I just wanted to show you that. All right, so I'm going to now show you the circuit prepared, which is all of those steps in the preparations have taken place. I've identified the nodes, okay, and they're nice in orange. I've selected a reference node. I put the reference at the bottom. I label the other nodes, V1 and V2, and then I insert current on the resistors. Again, the direction of these currents, left to right, right to left, totally arbitrary. There's no right or wrong in making them up or go down. So this is what I call the statement that I made earlier, preparing the circuit for solution. Okay. So at this point, how many unknowns I have? I have two unknowns. My unknowns are V1 and V2. So you expect to have two equations to work toward the solution for the two unknowns. The equations are going to be Kirchhoff current law at node V1 and Kirchhoff current law at node V2. Again, just side comment here. I am basically no longer going to be putting the plus and minus for you, but anytime you have, if I pick the current, let's say I1 going from left to right, you should cyclically in your mind see the plus and the minus here so that the sign convention, the passive sign convention is satisfied. But I will not be showing that. I'm assuming once you know the current going one direction, then you know where's the plus, where's the minus. Okay, so KCL at node V1, current coming in equal current coming out. In this particular case, all of the current are coming out. So I have I1. Again, realize this dependent current source is a current source, even though it depends on a voltage. It's a current source by nature of the arrow. So I1 plus 0.2 VA plus I3 plus I2 equals 0. Because that's the KCL at node V1. I highly recommend to students when you start doing this at first to just do a quick count on how many branches are coming off the node so that you make sure you have one parameter per branch so that you don't forget a current, basically. Okay. So that's KCL at node V1. At node V2, what's current coming into the node? I have I1 coming into the node, 0.2 VA coming into the node V2, and 5 amp. And then I have I4 leaving. So I have KCL at node V2 is 5 plus V1 plus 0.2 VA equal I4. And of course, in this case here, that was given the problem, given where I selected my reference node right here, then VA is where the, VA is the node where the plus is minus the node where the minus is. So VA is V2 minus 0. So VA is V2 for that problem, given my selection of the reference node. By the way, one of the nice things I tell students, if you want to practice, redo the problem by selecting a different node as a reference node. You're going to get different node voltages, but the solutions will be the same. In other words, VA will be the same, and the power for the 6 ohm will be the same. So these are my primary equations, the two KCL equations. And note again that I expect them to be in current, in terms of current, both of these equations. Then we're going to write Ohm's law. And when we write Ohm's law, that's when we talk about the sign convention, the passive sign convention. So these are the Ohm's law equations. So just be mindful here. When I put the current like I1 going from left to right, in my mind, I should see the plus and the minus here. For I2, the plus should be here and the minus here so that the current enters the positive terminal and so forth. Okay, so you should know that once you put the direction of the current on a passive element, that determine where your voltage is on that element in the nodal procedure. So I1 is V1 minus V2 divided by 6. I2 is V1 minus 0 divided by 3. I3 is V1 minus 0 divided by 2. I4 is V2 minus 0 divided by 1. Okay. And of course, we already came up with VA is equal to V2. So I'm going to take these equations and then put them in the two KCL equations that we just seen here and collect terms. Often this particular exercise requires you to put under the same denominator. So there is a little bit of a mathematical manipulation that you must do for that. But once you do that, you're essentially going to come up with two equations, two unknowns in terms of V1 and V2. This is the point that I expect you to simply go into your calculator, learn how to use your linear system of equations to solve for V1 and V2. So I don't expect you to do this manually. I expect this to be done. If you get the two equations correctly, I expect the correct answer to come out of that because you're using your calculator. So in this particular case, V2 is 5.14 volt and V1 is minus 0.17. Okay. Once I have the node voltages, I actually know everything about the circuit. So if I want power for the 6 ohm here, power for the 6 ohm is the voltage squared divided by the resistance. That's one of the formula for the power across a resistor. And the voltage across the 6 ohm is V1 minus V2. So the power for the 6 ohm is 4.70. And of course, we already determined that VA was equal to V2. That's 5.14 volts. So that actually concludes the problem. Okay. So this example is a pretty good one. It's a 3-node example, so 2 unknown. It has a dependent source in it, so basically start getting you ready to do this kind of activity. And it asks you to calculate power as well, which is a standard question that you're going to get in this course. Okay. Okay. So I'm going to stop sharing here, and I'm going to put a problem and ask you, again, I'm going to ask you to stop the video and then take about 25 minutes. You can take up to 30 minutes if you need to essentially draft a solution. What I want you to draft in the solution of the problem that I'm going to give you is essentially come up with n equations for n unknown. So let me show you. So here's the problem that is for you to do. Develop a nodal analysis procedure to calculate the power absorbed or generated by each element. So the resistors, of course, are always going to be dissipating power. And you have 2 sources. You have an independent source, a 2 amp independent source, and you have a dependent current source, that's 2IA. Okay. So I am going to ask you to pause the video for about 25 to 30 minutes and draft a solution to this problem here. And then we'll come back and see the solution here. So I'm hoping that you had a chance to work on this and were successful to come up with the set of equations for the set of unknown that we have. Again, when we talk about nodal analysis, we are talking about nodes. We are talking about node voltages. So the first part of node voltages is to accurately determine what are the nodes. This is a particular circuit that also has a dependent source. The dependent source is a current source by nature of the arrow that's inside of the diamond. So there is an independent current source to 2 amp, and there's a dependent current source to 2IA, and that dependent current source happens to depend on the current IA, which is under 1 ohm. Now the current IA looks going, it is the current under 1 ohm. So you don't need to put another current under 1 ohm once we get to the point of putting current on the passive elements. Let's find out what are the nodes. Again, I still want to make sure that you have the nodes accurately. So if I start here, so I'm going to say this is a node here, this is a node, and this is a node. Okay, so that's one node here. If let's say I start here for this, I'm going to say this is all a node, still the same node. That's all a node. Again, feel free to do this until you're comfortable with getting the nodes accurately, because if you don't get a node, nothing else works. So that's another node. And of course, I can start here. So I'm going to get nodes here. That's the node right here, right here. So that's another node. And then finally, I have a node here. So you can see, so how many nodes I got? 1, 2, 3, 4 nodes. Okay, so we got 1, 2, 3, 4 nodes. So I'm going to have 4 nodes in this problem. That means 3 unknowns. Okay, of course, the next step, I'm going to select the reference node. I'm going to label the other nodes, and then I'm going to put current on the resistors. Okay, but I wanted to show you that step, kind of doodling that step so that you can make sure that that is absolutely essential. You get it accurately. Okay, so let's see where we go. All right, so I select, of course, you see my nodes, nice dots, so that I have space to work with. So, but I just showed you how I would look at putting the nodes so that make sure that you get them correctly. So I put the reference on at the bottom right. So that means I have my three unknowns and I label them V1, V2, and V3. And then I put current on the resistors. Now, the 1 ohm already has the current IA. I don't add another current on the 1 ohm because that is the current IA. So I add currents on the other resistors. Okay. All right. So current labels, the direction of these currents, whether I6 is going left to right or right to left, totally arbitrarily. But once I put I6 going from left to right, I know my plus and minus are like that. So the voltage across the 6 ohm is going to be V1 minus V3. That is essentially how these two things syncs up, regardless of the direction of your current. If you apply the passive sign convention correctly when you do Ohm's law, everything comes correct. Okay. All right. So I have three nodes beside the reference node. I need three equations. They're going to come from where? I'm going to do a KCL at node V1, KCL at node V2, and KCL at node V3. All right, so there is a KCL at node V1. What current is coming in? I get IA coming in. IA is coming in, and then I get 2 amps and I6 leaving. So IA equal 2 amp plus I6. Of course, I tend to write the equation sending the constant on one side of the equation. That's why you see IA minus I6 equal 2 amp. But I tell students first, look at current coming in and set it to equal current coming out. That's easier to think conceptually when you write this equation, so make sure you write it correctly. KCL at node V2, what's coming in? I got 2 amp coming in, and I get I2 and I3 leaving. So I2 plus I3 equal 2 amps. So these are two of my three KCL equations. So again, I tend to write all my KCL equations all at once, and then I go into Ohm's law. So my third KCL equation is at node V3. What's coming in? I get I6 coming in, I3 coming in, and then I get I4 leaving and 2IA leaving. So I get I3 plus I6 minus I4 minus 2IA equal to 0. All right. So three KCL equations. Those are my three primary equations, and I'm going to go up to Ohm's law. And what Ohm's law does for me, Ohm's law allows me to go from current to node voltages by way of the passive sign conventions. So when I write IA, I look at where the current is starting, which is 0 minus V1 divided by 1 ohms. So that's why you see that. So it's 0, because once I have the current, then the plus is here, and the minus is here, okay, on the 1 ohm. So it's 0, where the plus is, minus where the voltage, minus where the minus is, so minus V1 divided by 1. Similarly, I2 is V2 minus 0 divided by 2. And then I'm going to go for I3 the same way. I3 is V2 minus V3 divided by 3 ohms. I4 is V3 minus 0 divided by 4. And I6 is V1 minus V3 divided by 6. So I'm going to take those equations, I'm going to put them into the three KCL equations. Often you have to put under the same denominator so that you can collect terms, so that you can have three equations in terms of V1, V2, and V3. When you do this, after a little bit of mathematical manipulation, you're going to get something like that, three equations for three unknowns. Okay. This is where I expect you to go into your calculator. Don't expect you to solve this manually. If you get these equations correctly in a quiz or an exam question, you will get 75 to 80% of the score. I'm going to grade you on the process, not on the final answer, just that. Okay. So solving this, you get V1 is minus 3.07 volt, V2 is minus 1.4 volt, and V3 is minus 9.49 volt. Okay. If you remember what the problem asked originally, the problem asked for power for each element. So we're going to calculate the power for each resistors, and we're going to calculate the power for these two sources. All right. So. Okay, so we're calculating the currents here. So what I decided to do here is calculate the current for each resistors. But the reality, let me just back up here. The reality, once I have the node voltages, I could easily calculate the power for each resistor. For example, for the 6 ohm resistor, I can say the power for the 6 ohm is the voltage squared divided by 6. So it would be V1 minus V3 squared divided by 6. So I could actually calculate the power for each resistors, basically. Okay. So, but I decided to just calculate the currents for each of those elements. Okay. Simply plugging in the node voltages. And then I'm using the power is equal to the resistance times the current squared. Again, that's an alternative formula for finding power for the resistors. I think you could have easily calculated that by using the voltage, the node voltages. But instead, I'm using the current squared multiplied by the resistance. So that's the power for the first, for the 1 ohm, the 2 ohm, and the 3 ohms, and for the 4 ohm and the 6 ohm. Okay. So the next part that I want to spend a little time discussing here is how do we find the power for the two current source, the independent current source and the dependent current source. Okay. So let's deal with the independent current source. So remember, for sources, we must use the active sign convention. That means the voltage for the independent current source has a polarity that I'm showing here. The plus is on the right, the minus is on the left. So the power for the 2 amp source is going to be voltage times current. So we know the current is 2 amps, so it's going to be 2 amps times the voltage. The voltage is going to be V2 where the plus is minus V1 where the minus is, following the active sign convention. Okay. For the dependent source, the plus is here and the minus is here, so that the current enters the negative terminal. So again, the power for the dependent source is going to be the current times the voltage. The current is 2IA, and the voltage is 0 minus V3, given the polarities that I have. So that's the active sign convention gets satisfied. And that's what I do here. Okay. So for the 2 amp source, the power is V2 minus V1 multiplied by 2. And for the 2IA dependent source, the power is minus V3 multiplied by 2IA. So we've concluded this. And that also concludes our mini lecture on doing some examples, some pretty robust examples in terms of nodal analysis for circuits, DC circuits that have no voltage sources. The next lecture, we're going to cover what does it take to handle general circuit that is with voltage sources.